It's a pleasure to introduce Dr. Varadhan. Dr. Varadhan is in Biomedical Engineering Group at IIT Madras. He completed his BE from in Electronics and Communication Engineering in 2002 and MS in Biomedical Engineering in 2007, both from IIT Madras. He then did his PhD in kinesiology in 2012 from Penn State University. Kinesiology is the scientific study of human or non-human body movements, and it addresses physiological, biomechanical, and psychological mechanisms of movements. So Dr. Varadhan's research is on movement neuroscience, motor learning, co-articulation, novel computer methods, input methods. His group has developed a novel touch-based text input device and a data glove to record hand postures and movements. Future applications for his work include novel input systems for gaming, entertainment, and animation industry. Dr. Varadhan's group also has developed algorithms for detection of hand movements using a small number of sensors that can be a boon in human-computer interaction and gaming industry. And looking forward to an interesting keynote. Over to Professor Varadhan.
So what am I going to be talking about? I'm going to be talking, for this particular talk, I'm going to be focusing on how we can use movements, specifically hand movements in this case, to communicate with systems, to communicate with computers, but any system, it can be a phone, any other system. How that can be used in entertainment, what are the potential applications? We haven't developed the applications, but I'm just going to speculate about what else is going to this. But I'm going to focus mostly on the core of how to detect and how to communicate, but not develop the apps for the entertainment and gaming. So I'm going to be focusing on that, and that's my team. So that's my team. So I have a bunch of PhD students and a bunch of MS students. Actually, 3 MS students, 3 PhD students, a couple of research staff, and some dual degree students. Most of them are brilliant, amazing. There's some different students are different, but most of them are amazing students. They are very hardworking. So here are some toys that we use in our research. So for example, that one, right? So that's the ATI Industrial Automation's 6-axis force transducer. So slightly away from what's going to be the focus of today's talk, these detect forces and moments about all the 3 axes. We have a set of 5 of those, and we fit this on objects that can be grasped to study the force patterns that humans use while manipulating objects. So in other words, dexterous manipulation by humans is not the same as robotic manipulation. So how do humans coordinate their fingers forms half of my research. We have a set of 6 of these. One I use for measuring fingertip friction. The other 5 I use for measuring the 5 fingertip forces. These are terribly expensive. A set of 5 of these costs as much as a Mercedes. So pretty expensive, thanks to IIT Madras for its seed grant. This I was able to get this toy. The one here, we're going to focus on that one. That's the Polymus Liberty 1.8 mm tracking sensor. That measures displacements, angular displacements and linear displacements in all 3 directions. Again, pretty expensive. I'm going to be talking about that in a bit. And these, excuse me, These in red are the things that we developed. This is technology developed by us. This is the glove that we developed and how that's used to communicate as a text input device and stuff. We have been relatively successful in taking this from I'll show you the individual evolution, the steps of making this glove, how it was like some 3-4 years ago, and how is it now. It's close to being a product. So I'm going to be talking about that too. And that's the other one you're seeing, the yellow one, for example, that one is the visual occlusion glass that I use for behavioral neuroscience experiments unrelated to this, to today's talk. So the question is, what are the challenges in modeling human movement? So what's the big questions that we study? I'm still introducing myself. So what the big questions that I ask in my lab that I'm focused on, how does the human brain control movements? You see, for me, if you had seen the first slide, I say life is movement and movement is life there, right? So that's our lab motto. So there is this manifests itself everywhere, because the absence of movement is basically death. Because it turns out, and this is true philosophically, this is true from a mechanics viewpoint, this is true from an engineering viewpoint, this is true from practically every viewpoint. Even at the micro level, for example, right? Change of the conformation of proteins is considered, or change in structure of proteins is considered as life. That doesn't happen in dead bodies, or at least not after a few days after death. It happens for the first few hours after death, but not after that. So in other words, movement is the very life for all of us. Life itself is, if you're not able to move, then you are, that's something that you can yourself feel when you have a sprain, for example. When you have a little motion restriction, you feel how difficult it is. And imagine there are thousands of people who need help with movements. That's the motivation for us to do this. So there's this continuum of movements. We work practically in the entire continuum. What do I mean by that continuum? So normal people, or a person like me who has no particular motor skills. I'm not a sportsman. I'm not a musician. I don't do this. The only thing I can do well is studying, which I do well, by the way. But I don't play cricket, I don't do any sports, I don't play any instrument. So these are the so-called normal people. These guys fall in the middle of this continuum. Then at the left extreme of this continuum, you have people who need help with movements. These are patients of neuromotor disorders. These are people with Parkinson's disease. These are people with stroke. These people need help with movements. There must be a device or something that or a rehabilitation approach we should develop to help these people. And there must be people, and then there are this, what I call as the super dexterous people. That's like Roger Federer. That's like this, exquisite Bharatanatyam dancers. These are the people who can make exquisite, very nice, graceful, or particularly strong movements. Now, can we come up with learning or training algorithms to improve learning in people, in athletes or in artists? And can we come up with rehabilitation algorithms or approaches for people with this? And can we do that by studying healthy people, normal, what I call as typical people? People who have no particular skills but can do activities of daily living, can brush their teeth, comb, but not actually perform any particular motor act exquisitely. Normal people. Can I come up by studying normal people? Can I say what's going to be the how to help the others? That's the big question that we are studying. So those are the big questions. How does the brain control movements? Why study movements? I have already said why study movements. The other question is, how does the brain control the relatively large number of variables, the number of variables that the system must control, if it is controlling. The question is there control? That's a more philosophical part. Does the brain even control? That's the question. Some people ask. It's possible that this could happen in, in systems that are passive. that debate we'll reserve for later. Maybe the system doesn't control. But if it controls, then it has to control a lot, because there are many variables. For example, in the case of fingers, right, the number of variables that need to be manipulated is more than 5, is more than 10. Especially when you're holding a cup of coffee, when you're holding a glass, right? So the variables, the mechanics requires that you must be in a position to manipulate at least 5 to 10 of these. And we do these tasks all the time, every day. How do we do this? Nobody knows the answer. We are trying to find out how. So these are the reasons why we should study this. How to detect movements? What's the application? Well, that's the application. So there you see a person, doing an act, and it's presented as if the person is walking on a different planet. And then what's the application in the entertainment industry? Well, you know what's the application. So here you see, that's Tom Hanks, of course, right? So you know Tom Hanks. This is from Polar Express. The movie itself is not great. That movie is just okay. But you must definitely watch the movie for the animation. It's amazing. The movie is boring, but the animation is truly amazing. So Tom Hanks is speaking, and that's as if the train conductor in Polar Express is speaking like this. And that's Bill Nye in Pirates of the Caribbean, and that's Zoe Saldana in Avatar, of course. So what does this represent? This is the movement capture possibly from using passive recording systems for movies, entertainment from an animation viewpoint. We will talk about that in a bit. And then in sports and gaming, right? A very successful. This is the Kinect ones, right? So again, what's the requirement? What's the need compared with the accuracy requirement? So what's the some movement detection is sufficient, or is very accurate movement detection needed? So as the accuracy goes up, as the resolution goes up, then the price also goes up, right? Obviously, so you cannot have everything. So Kinect, for example, are relatively, when compared with the systems that we use in the research lab, are relatively, priced, competitively priced, very low priced compared with what we do, right? But we need the accuracy. Kinect doesn't need it. So where do you set the bar? Where do you say that this is sufficient and not more? So, but here is sports biomechanics. You have this sprinter. So what we are looking at in the research lab are these. These are our interests. Here is the sprinter who is running. The ground reaction force on the toe is 2,000 newtons. And we are interested in studying the kinematics, the joint angles as they change when the person is running. The person has so many markers on the body, and that's bowling. So this is baseball bowling and baseball batting, not cricket batting, baseball throwing, and this, and the one in the bottom, the one in green that I'm going to now show, that's bowling, right? Here, so this is research lab grade work that requires more accuracy, that requires a higher resolution, and this is what we do in the lab mostly. But we want to go here. We want to do these. We want to develop tools for these by studying these. Can we develop toys? Can we develop tools that are relatively inexpensive, that can detect movements, and algorithms that can detect movements, and present the output to a computer? So that's the question. The science is all great. The science is all fine. But I'm talking about technology development. Can we do that? And again, what are the various devices? What are the various options that we have? Before I move on to the technology development part, what are our options? Well, here on the top, you see OptoTrack. That's an active LED marker-based system. Just costs 70 lakh rupees, relatively cheap. Now it's bought over by the Northern Digital Corporation. Before that, it was called OptoTrack Corporation. Doesn't matter. Whoever wants it, it's still expensive. It's about $90,000. So nearly 100,000 after customs and stuff. So you're talking about 70 lakhs. After all duties, GST on the duty, so everything. Active LED marker-based system, that means more accuracy. So what this means is that each LED comes with a unique frequency. So there isn't a possibility that, different markers can be mistaken to be another marker. So if I put a given frequency, marker of a particular frequency, say on the wrist, and a different frequency marker, say on the elbow, or whatever, on the forearm, right? Those frequencies are going to be detected by these cameras. So it's impossible for me to mix the markers. However, well, with that, that's a great advantage. That's not a small advantage in motion capture. It's a great advantage. But the cost is very high. At the low end, you have these animation grade cameras. I don't know how they came up with the name. It's called OptiTrack. And you realize immediately that in the keyboard, in the regular QWERTY keyboard, I is just next to O. I'm not saying they stole the name. I don't know what happened. But this is OptiTrack. Very inexpensive systems. This is more like 5 lakhs. You could have a 6-camera system. But this comes with passive reflexive markers. In other words, you put markers, and it is your job as the experimenter, as the technician, to find out, to say, hey, that is not the hand marker. That is actually the elbow marker. Because all markers look the same for these cameras, because they just reflect light that is incident on them. Whereas the active LED markers transmit light. So fundamentally different procedures, right? Fundamentally different. But other problems in passive reflexive systems, right? The advantage is that they are not tethered. So I could just put a marker and the person can move freely. But in active systems, if I have to send a frequency out, then I need power, I need energy, I need to power them, I need battery, I need everything. So then they are tethered. Then the question is, can I get accuracy that I want? Or is the tethering going to prevent natural movements, for example? That's the other question. So if I just tie the person up and then say, move naturally, then how can they move? So that's the other question. So you want to find a sweet spot. You want to decide, what is the accuracy that you want? And what is how much are you willing to pay? So in the bottom, you see this OptiTrack animation grade camera system, passive marker system. So that means what? So a lot of, for us, when we do PhD, a lot of hours, tens of hours, hundreds of hours, tens of hours every day practically are spent on what is called as tracking. We finish an experiment, and what we do, we come in the morning to the lab, and we click, 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 click. This is this marker, this is this marker. You keep doing this. After some time, you become crazy, because all you see are dots. All you see are dots. You only see dots. After some time, you just get up from the computer, you see a whole bunch of dots, because there's a lot of manual work. Algorithms are, by the way, to be honest, algorithms are now available to do this. Still, there is no algorithm that can match this, that can do what we can do. It would be nice if we could do it. We want to do it, but yet a lot of time for graduate students, because as we joke in the grad school, it costs less to fund a graduate student. They pay you peanuts, right, as a PhD student, than to buy OptoTrack, right? Obviously, why would I buy OptoTrack when I can just fund you for a few thousand rupees? Why would I do that? Just spend the time, dude. And that's good. We learned a lot. That way, we learned the basics. That's good. But there is a lot of manual work that is needed. Analysis means manual work. You go step by step, you go frame by frame and identify each marker. Say this is this, this is this. And imagine you are collecting data at 100 hertz. You are collecting it for so many minutes. I'm talking about hundreds of thousands of frames. And you are collecting it for so many humans. You are collecting it for 12 subjects. Each person is doing the task for 1 hour. You are collecting at least 100 hertz. I mean, you know what, 3,600 frames for one person. I'm talking about several thousand frames. Processing them manually is a clear pain. But that's our day-to-day job, a lot of it. It's still algorithms haven't come to the point where we can completely depend on them. For example, if I give this and the student says, I have this algorithm that can do this, I won't trust him. I'll say, I'm sorry, I don't trust it, do it. Then the students still try to convince me that, no, this is awesome. This is not the old algorithm that you had in grad school. I say, nah, just do it manually. Because that they are there, but they are not as sophisticated as they should be. Algorithms exist, so that's one. So as I said, to recap, so there are two types of marker-based capture systems. One is active LED-based marker system that is tethered. That comes with the advantage of accuracy. No need of tracking. That's the great thing. Tracking is automatic. Tracking is inbuilt. In other words, because I know that this frequency is coming from the hand regardless of however difficult it is, whatever is happening, whatever complicated movement you make, the system will always correctly identify the marker because it is frequency locked. It is tied to the frequency of light because it is the marker that is sending the frequency. In the bottom, you have this is the other extreme where you have to do the work, but it is less expensive. It's only 5 lakhs. The one in the top is 70 lakhs. What I have not spoken about is the middle ground. The middle ground is active LED-based marker systems with manual tracking type. That doesn't come with software. That is the type, I haven't put the picture here, phase space type of system. PHASC. SPAC, phase space, that's the name of a company. They make it for like 30 lakhs, about 30 lakhs. That was 2014. My colleague got this for her gate lab. So that's the middle ground. In that case, you have grad students who can do the analysis, but you want the accuracy. Then that's great. So those are the marker-based systems. Then you have markerless systems, systems that do not use a marker, but other technology. This is what we use in our lab for other reasons, that will become quite obvious in the next few slides, is what this does is these are 1.8 mm diameter systems, sensors, that these are electromagnetic trackers that have coils that work on the principle of induction, that produce certain, so there is a transmitter from which that transmits, that works in tandem with these sensors. So uniquely for each sensor, there is a magnetic field that is change. So the science behind this is way complicated, but what we get out of this is the very accurate displacement information, linear and angular displacement information. These are like a super accurate system. The resolution is like 1.27 microns. The static accuracy is about 0.7 mm, so about 700 microns. Very accurate systems, thanks to Department of Science and Technology for funding this toy for me. So DST through their cognitive science initiative gave me a lot of money. By this system for 16 sensors, we put on each individual segments of the finger. So if you see, we have in each finger 3 segments. So that's 3, and we have 5 fingers. 3 times 5 is 15. Plus we put a reference marker on the wrist, reference sensor on the wrist to measure all the displacements are measured with respect to wrist, because I'm not only moving the fingers, I'm doing that. So when I do that, it's not my index finger alone is moving to that point, but rather it's the arm that is moving. To subtract the arm movements from the finger movements, we use the reference sensor. The math I'm leaving out for the purpose of this audience. But there was a time when this was not available. And then what happened? Before this was available, we wanted to still do this sort of work. I'll talk about what we did at that time and where this landed. Then there are other systems that talk about, that help us with capturing movements, hand movements in this case. These are data gloves. Again, with accuracy, with data gloves, the problem is, these use, many of these, almost all of these use elastomers. So they use, there are two technologies. One is resistive bend sensors. So what they do is, as I move a finger, as I bend a finger, the sensor, so you wear a very snug glove. By the way, for different humans, because the hand size varies, you have to buy multiple sizes of those. Imagine doing that. This is, for example, Cyber Glove is the most popular one of these. It costs about $20,000. If I have to get 3 of these, I'm talking about $60,000, a lot of money. I'm talking about 36 lakhs. I'm talking about 40 lakhs. So again, we'll have to still decide what to do, because gloves, I cannot change the person's hand, but I had to, if it's not snug, then there'll be relative movement between the fingers, between the underlying rigid body and the glove, which is undesirable. But on the other hand, I cannot buy 10 such gloves. You'll have to find the sweet spot. You'll have to find what to do. But anyway, the technology is the following. The technology is that when I bend the hand, the sensor also bends along with, if I wear a snug glove, the sensor also bends. And the resistance of this cable changes, and that's supposed to be linear, and there is a linear relationship between the bending of your hand and the bending of the sensor. That's using very sophisticated algorithm, they detect what the joint angle is. Problem is that accuracy is compromised, because you have to trust the organization, you have to trust the vendor. When they say this is the accuracy, you have to, for a person like me who is sciencey, I question everything. Really, this is the accuracy? How do you know? Like, there isn't a way. You have to take their word on it. So that's a problem. And the other problem is their calibration for each hand is tedious. You'll have to, so it's not like I can wear the glove and then you wear the glove, the measurements are going to be equally accurate. No, they won't be. Because calibration, I have to calibrate it for my movements, I have to calibrate it for your movements. So before you can do any movement detection, we have to first calibrate it. We have to force them to this, and that procedure is very tedious. So that's the thing, and there are many. So Cyber Glove is about $20,000. There are these 5DT gloves. They're relatively cheap. What I would call as animation grade glove system was about $5,000, including software and stuff. But less number of sensors, less accurate. 14 sensors on the Cyber Glove, 14 sensors on the 5DT glove, 21 on the Cyber Glove, and so on. What we did was, and then again, elastomer based fabric. This again, there's a linear relationship between between the hand movements and the aperture, so and the electrical properties of these materials. Again, problem, non-linearity is associated with this, requires calibration. So this was the situation way back in 2014 when we did not have the funding to buy this fancy toy that I showed in the previous slide. So here is this fancy toy that we now have. But back in 2014, I didn't have the money, and but I had a brilliant student. So Nayan finished his MS recently, completed just a few months ago, just graduated 2017. He was there, and we wanted to do this glove-based detection or hand kinematic detection. He wanted to develop algorithms. He wanted to develop the toy. I told him, we have submitted the proposal, but we don't know whether we'll get funded. The first proposal was ditched, and by the time the second one came through, it was 2015. In the meanwhile, we didn't want to have an excuse for for that we didn't have funding. I told Nayan, why don't you just try this? Why don't we do something else? So what Nayan did was, he I just told him. I didn't really say, you must do this. Why don't you do? Some students are super motivated, super brilliant, so, exceptionally brilliant and motivated student. So what he did, he took that as a challenge. He took it super seriously. And what he did was, he took these IMUs. So he took this, this is LSM 330 DLC. I think this is from ST Microelectronics, I think. IMU, there are many actually. Again, there are many, but we took this and we took this board. I think this is from Texas Instruments. And so he got the chips. We developed the PCB for each finger segment. Basically, when I say we developed, we did everything. We did the entire electronics. So we did the fabrication. We did this. We got it fabricated. That is from a company in Bangalore again, from somebody who did it for us. And we connected it through cable. So, and the question is then what we did, we wanted to, but what these measure, IMUs measure accelerations and angular velocities, for what it's worth. Just to remind you, IMUs measure, these are accelerometer gyroscope systems. So they measure accelerations, linear accelerations in 3 directions, and angular velocities in 3 directions. So the question is how then to convert this into, because we are interested in positions. We are interested in displacement. So again, so what's acceleration? Acceleration is double derivative of displacement, is it not? So if I want to come back, then you'll have to integrate. So what Nayan did was he actually developed this algorithm for this. Relatively, this we developed ourselves. So he computed. So we take a window of this. So here, for example, we used a window size of 50, and we converted this acceleration first into velocity, and from velocity into position. Agreed, that isn't going to be great accuracy, because integration comes with constants, because when I integrate, there are constants and we don't know what these constants are. There are problems, it requires calibration, but this is cheap. We got this for a few thousand rupees. I don't have to spend lakhs, and this is all I could afford. And then there are then by the time we developed, there were other algorithms, very sophisticated algorithms. This could do this for us. One popular algorithm now, not at that time when we developed it, is this Madgwick's algorithm. Those for people familiar in the field, they can recognize that that's the Madgwick's algorithm that can convert from accelerations to displacements. Okay. So what Nayan also did was he modeled this system in 3D. So we wanted to study the individual finger segment kinematics, individual segment motion. Note, our interest is research. So that means we are interested in developing relatively accurate kinematic models of the hand. So what Nayan did was we took each finger, we considered each finger as a 4-degree of freedom system, because each finger can bend and go back. And it can also move sideways. These are called as flexions and extensions, and these are called as abductions and adductions for technical names. So I have 4 degrees of freedom in each finger. That's 4 times 4, 16. And the thumb has 5 degrees of freedom, because I can do that. I can do that. I can also do those. I can make 5 movements with the 5 independent. Actually more, but for this purpose we considered this to be 5 degree of freedom system. So the total number of degrees of freedom considered in our system was 4 times 4 is 16 plus 5, 21. Actually, what we did not consider, we should have considered that, but we did not have the electronics, the system that should have done that. That is the palm arching. So when I do that, there is a very small amount of this movement near the little finger when I do that, where, when I do that, when I touch the tip of the little finger with the tip of the thumb, what happens here is not just the finger moves, but also the palm slightly arches. This happens only in very specific movements, but that's a degree of freedom that we did not consider, because we didn't want to, we had relatively, large set of data just from the other movements. So we didn't want to consider this to be a super sophisticated system. That is also difficult for us to model, and data analysis is very tedious. So we had 21 degrees of freedom, and we had two sets of tasks, those we call as externally, for technical names, externally constrained postures and internally constrained postures. What do I mean by that? External constrained postures are holding objects of different sizes, different shapes. This may be a coffee cup, this may be a scissor. By the way, we had to, our system is an electromagnetic tracking system, so so our lab cannot have any metals in it. So we have to work with wood, plastic completely. So all the objects, we got, plastic scissors, we got plastic knife, we got everything in plastic. So what would you do when you cut with a knife? So for example, how would you hold the knife? How would you hold a scissor? But because scissors, knives are obviously made out of metal. But we got everything, a whole bunch of balls, a whole bunch of stuffed toys. These are available from any regular toy shops. So that we got as objects. Then we ask people also to assume postures, that have specific meaning. For example, in sign language, for example, in American Sign Language, different, for example, saying that means see in American Sign Language. I know only 2 or 3 such symbols, so don't worry, don't ask me the others. That's see, for example. Likewise, so that's postures that are not constrained externally. There isn't an object that I'm holding. And to add more complexity, and we liked this, we also analyzed Bharatanatyam mudras. That was way complicated to do because some of the mudras are extremely hard. For example, that I cannot do it properly. I told you I'm not specially gifted for arts. Something like that. We didn't have subjects who are trained in Bharatanatyam, so we had to train the subjects to do this. One particular girl was super fast in doing that. We then asked her, hey, do you know Bharatanatyam? Yeah, I dance. I perform all the time. She was super fast. The normal people cannot do it so easily. So there were like 20, 30 Bharatanatyam mudras, and there were like the American Sign Language, and there were the objects. In total, about 100 different postures. We collected this data for about 5 seconds for 5 trials of each of this object, and for 5 seconds, a very tedious experiment. And I'm a very tough taskmaster, and unless you show that there is sufficient statistics, I'm not going to accept anything you say. So Nayan worked super hard on this. It took 12, he worked with 12 humans, as in 12 subjects, 6 males and 6 females, and getting the ladies to the lab was tough for him, and tough. 500 trials because there were 100 postures. Each was performed 5 times, 500 trials, and the instrumentation time, because these electromagnetic tracking sensors are also tethered. Remember, because they come with a cable, I have to put the sensors with cables. The instrumentation time was close to 25 minutes. So the total experimental time, and by the way, if the subject wants to go to the restroom, let's assume this happens, right? It's biological need. What do? Well, ethics requires that you let them go to the restroom, of course. So then what happens? Another 25 minutes of instrumentation time. Very tough experiments, these. The total experimental time for each subject was about 5 hours, 4 to 5 hours. We told the ethics committee that it was only 2 hours, so don't tell outside. We finished it in 2 hours flat. As in one session. Okay, let me clarify that. We performed the experiment not in one go of 5 hours. Nobody can tolerate that. So what we did was we performed it in 2 sessions, each lasting about 2.5 hours. So that's how it was. So one day the subject came, did half of the experiment, then they went. And another day the same subject came, did the other half. Again, the problem with that is that, after one day they are scared, they don't want to see your face, they escape finished. That the entire data you have to drop, you have to collect one more. So very painful experiments. But let's just say that this student was very motivated. He was like super hardworking on this. He somehow chased all this, he finished all these things, and that's not the end of the story. So this is what we did. This is the experimental setup. These are the various places in which we place the sensors. In other words, we place sensor in every segment. And while analyzing the data, our data was collected according to the according to the biomechanical requirements. Those are the axes that we use for that purpose. And what Nayan found was that there was and not all data are, when I say there are 21 degrees of freedom, not all degrees of freedom are independent of each other. We must assume that the system somehow controls this with a smaller number of variables. I'm going to call, without defining it properly, I'm going to call the smaller number of variables that are used as synergies. So if anybody wants to talk about that later, I can talk. But I'm going to call, so in other words, the system combines, the brain probably combines many independent degrees of freedom into one independently controllable component, which we call as synergies. There are other definitions. For this purpose, for this audience, I'm going to define that as synergies. And there are many ways of computing how the brain probably, again, we are not saying this is how the brain works. We don't know that. We don't know what the brain does. Nobody knows, luckily, fortunately. But we are looking at it from a computational perspective. Here is the data, and is there some, synergies? Is there some, opportunities for us to explore this using approaches, linear and non-linear synergies approach we did. And we used a very simple, straightforward algorithm, principal component analysis, and we found, yeah, there are synergies. Actually, the hands for these postures are controlled by about, you could say, about, that, right? About 5 to 6 synergies are sufficient to control these 21. Because why? That's approximately the point in the scree plot. So if I draw a scree plot, and that's where the line becomes straight, approximately. So note, of course, I will not get the same accuracy as I did when I include all the 21 degrees of freedom. But you have to, there's a trade-off between complexity and accuracy. You have to decide what you want. Because if I had 21 degrees of freedom, then computation becomes, that much harder. And then we changed these into common postures and special postures. Postures that are performed by everybody on a daily basis, we called as common postures. These are different from the earlier ones that I defined. I defined these earlier as extra. It's on. It's on. So these we called as special postures, and we found that the first 3 principal components, if we take, there is a difference in the way the system approaches common postures and special postures. Right? Again, what about reconstruction? Reconstruction errors. Again, as you add more synergy components, as you add more principal components, you get. So I'm interchangeably using principal components as synergies. For this purpose, it's okay to do that. So as you add more principal components, the accuracy improves, or the root mean square error goes down. Okay. The other way of doing that is using autoencoders. So these are neural networks. Here, the problem is this: we don't know. We like to know everything. Here, what we don't know is what happens in this layer. This is a hidden layer. What happens in the hidden layer is something that I won't say we don't know. It's very difficult to compute. It's so thank you. So it's tough to compute. It is possible. It's not impossible. Everything is possible. It is tough to compute what happens in the hidden layer, but it's possible with some work. And Nayan actually did that also for us because, as I said, I'm a tough taskmaster. I said, I don't know if what you're saying is true. Can you go and take a look at the hidden layer and see what happens? And he did that with sufficient pain, but we did it anyway. And we found what actually happens. What actually happens is this. Of course, this is the math behind what actually. So we use a sigmoid for our neurons. So doesn't really require elaboration. Most of you probably know this already. So we used a log sig function for our neurons, transfer function. And surprisingly, what we found was the results were very similar to the linear method, the principal component method. So we thought, what's a big deal? I mean, it's not, you don't get extra credit for going through so much pain. So, but on the other hand, what we also learned was that if you had multiple hidden layers and multiple neurons, a very large number of neurons in the hidden layers, if you had 2-3 hidden layers and 50 plus neurons in the hidden layers, you get very high accuracy. But computationally, these algorithms take months to converge, because the student came and says, hey, you know what, I got an accuracy less than 2 degrees, you want me to stop? I said, no. Unless it converges, I don't want to trust. These take months to converge. These on like very high-end processors, I mean, on the clusters, whatever. I mean, they take several weeks to converge for one subject, for one person. And that will have to run for 12 subjects. 9 actually gave up on that. So we accepted accuracy less than 2 degrees as something that we did. But we are now rerunning this algorithm. So he's now working here, and he's working for analog devices here, and he's still running those algorithms from remotely from Bangalore in my lab. Actually, these computers, I said, these workstations and clusters are in my office. There is no other space to keep it. So my office is super hot. Either it's super cool or it's super hot. There's no middle ground. It's always hot because of this, these workstations that keep constantly running. They do this number crunching forever. For one subject, it takes, now we have been able to bring it to a week, but still we are talking about 12 weeks for 12 subjects. We are still talking about a relatively complicated, relatively tough thing. But our accuracy with a large number of neurons and a large number of hidden accuracies, hidden layers is about sub 1 degree, like 0.5, 0.7 degrees, are very accurate models with less number of components. So that's like, I am able to predict what happens in a 21 degree of freedom system with 6 degrees, actually 8 degrees of freedom. Actually 8 degrees of freedom with 8 independent sensors. I can predict what happens with 21 sensors with half a degree accuracy. But this takes time, investment of computational resources. So it's not trivial. So these are the various things. But which 8? That's the other question I asked. Which 8? He did more than an MS. He did close to a PhD. Let's just say that I failed to convince him to continue a PhD. He was attracted by the industry, so that's good. They probably paid him a lot of money, and that's good too. So he also asked the question, which 8? It's okay, 8 sensors are important. Which 8? And that's not a trivial question because there are 16 of them. Choosing 8 from 16 is a 16 choose 8 problem. There are so many ways in which it can be done. How, and remember, it's not going to be the same for all people. It's not the same 8 for all individuals. It's probably different 8s. So that means there must be an objective method for us to guess this. How much time I've got? Okay. 5 minutes? Few minutes? Okay. So what this is the algorithm that we used for synergy, finding representative postures. What we found was that some postures are representative. These I'm going to call as, the eigen postures. These are the postures from which if I make small changes, I'm going to get other postures. So this is what I found. And this is the very complicated algorithm. I could explain this if I had time, but there is no time. What we did was that, briefly, what we did was that we found correlations between sensors using regular correlation techniques. And if the 2 sensors are correlated, we dropped one of them. Because, these 2 sensors are correlated. If one increases, the other increases. If one decreases, the other decreases. Or correlated negatively. If one increases, the other always decreases. That's relatively rare, but that could happen too. So if 2 sensors are correlated, one of them need not be part of the, included in the analysis. But the question is which one? To find out which among the 2 that are correlated is important, we use a different technique. What we do is we perform an analysis of, we include a sensor and we find the networks, the neural networks accuracy, output accuracy, and then we remove that sensor. Right? When I remove the sensor, if the error goes up by a large amount, then that sensor is important. So we use that sort of again, that means I'll have to run this so many times. I'll have to do this multiple times. Because there are many ways in which you could, out of 16 sensors, there are many ways I can take and remove a particular sensor. There are too many ways actually in which that can be done. A very tough thing. So, but we did it anyway. I mean, we did the good old way. We did all the possible options, and then we found we found the root mean square error. Whichever sensor upon removal gives the largest root mean square error is an important sensor between the two correlated sensors. So that sensor is kept, the other correlated sensor is removed. And we perform this iteratively over the 16 sensors. And because we set a hard limit of 8, above 8 I don't want. I want to do this only with 8 sensors. That was the constraint. So we repeated this. We continued this business multiple. So we ranked the sensors in the order of their importance using basically mean square error. And then we found correlations and we performed this. That's the brief outline of what's going on. And this is our own data glove. This is probably having some importance for you. This is not going to detect joint angles. This is going to detect events. So here we built a text inputs device. This was developed by my PhD student Dhanush. So what he did, so here is the evolution of this. There are like, I don't know, 9. Actually, there are 17 versions of this. There's no space to put all 17, so we just decided to put 9, a hard constraint. The one you see in number 1, right? That one is was built way back in 2013, I think, 2013. And then you see the improvement. So that used cables, that used wires for communication, for between each. So what we did, we had patches, conductive patches, and that were connected to cables, and that were connected to a microcontroller. I'm going to talk about that in a bit. But as it improved, right, what we did, we went on to other technologies. So we moved on from cables, and we used conductive threads and conductive fabrics for this. So the glove looks like a real glove for anybody. If you wear it, you won't even know that this is being used for this purpose. But we can detect, touch of different points with this. So this is probably very, very useful in gaming, or so where you only need 5-6 points, 5-6 buttons. You only need so, other than the sophisticated games I'm talking about. The regular games need about a few buttons. There is no tool that's as good as this tool. This is the best tool. Because if you didn't have this tool, we cannot use tools. Remember, any civilization, any building, imagine there was no hand, right? This building couldn't have been built confidently. This computer nothing could have been done. So this is the best tool. So we wanted to use this tool for this purpose. So that's one application. So what we used was, so this is the microcontroller that we use. I'm skipping this slide for want of time. We use the regular, general purpose microcontroller. This is TNC 2.0++, I think. One of them is 3.2, not the same. I think I'm able to see they're not the same. One of them is 2.0, the other one is 3.2. And so we used, conductive fabric, and it is stitched. Again, very tedious work. You have to stitch the cable through the cloth, through the fabric. We did this for every subject, and to type and play a game, for example. So this is a glider game. This is a typing game that we bought from online, some platinum typing tutor, something. Where, if you just touch different points on the glove, when I connect it through to the computer recognizes our system as a regular, a generic USB keyboard. So I type different text, and it goes out, and I keep typing. The goal is to keep this glider from falling down. You improve in typing speed, and this. We are sciencey questions there. This is what DST funded me for, how co-articulation is developed, how smooth movements are developed. That's the question that I proposed I'll study for DST cognitive science. So this is what they want us to study. Co-articulation means what? Smooth movements, or how expertise in performing movements is developed. That's the question. How is motor skill acquired? That's the question we are studying with that. But I'm talking about the text input device that is being used. So that's the experimental protocol that is being performed, the science part of it. But the device is used for science, but it can also be used as a regular consumer. But we haven't yet thought about what to do with it. We want to commercialize it, we want to patent it. We haven't thought about this. By the way, this is not rocket science. Anybody can do this. These are not, you just go to Google and type, I don't know, glove-based typing. You'll see 1,000 Kickstarter projects or whatever. There are just so many of those. So we didn't invent this in other ways. But we have sufficient experience with this that we are able to, that only we can do this. So I can show you this picture. You can see all you want. But the details of how this is done, because 4 years of experience. So it makes a difference. So that's the question. Thank you so much for your patience. I don't know if I was over time. Thank you so much for your patience. And funding for us comes from my seed grant from IIT Madras. Very generous seed grant. Thank you. Thank IIT Madras for that. None of those results were presented in today's talk though, but thanks anyway. Department of Science and Technology, Cognitive Science Research Initiative, again, very generous grant. Thanks so much. It really made a big difference for our lab. And that markerless based system, the Polymus Liberty tracking, electromagnetic tracking system cost me 35 lakhs and was sponsored by Department of Science and Technology, Cognitive Science Initiative. And BIRAC, as in Biotechnology Industry Research Assistance Council, is proposing, the money has not come yet, we're still in negotiations, they want me to start a company, yes, I'm still talking about that, for development of a device for tracking Parkinson's disease. That's science, that's rehab type of work. And my research scholars, Dhanush, Bala, Bhanuti, everybody is Jai, Ann, Ram, Pratham, Neeraj, and Akash, Niranjan. There are 2 Niranjans, so there used to be 2 Niranjans, so I call Niranjan as Akash. And a majority of what was done, what was presented in today's lecture from 9 but. So thank you for listening. Thank you so much for your patience. I'll take any questions online or offline, whichever way you guys want it. Yep. No. Oh, so the 16 are on each segment. Okay. So I have the ground truth. So I know that these are the 16. So each segment has one sensor, and that sensor can measure, linear displacement and angular displacement with very high accuracy. Now, which 8? That's a very good question. Which 8? I told that which 8 is going to be different for different humans, because it turns out that the same posture can be performed in different ways, and that's why I have a job. If you were all robots, if we were all robots, I won't have a job. Thankfully, we perform. There's a myriad number of ways. There is flexibility of doing motor tasks. And that's what gives us an opportunity to exploit which particular solutions are more important, which particular solutions are, can be trained, so to speak, in athletes and artists, in people with neuromotor disorders. So that's why, as I said, I have a job. So which 8? To that question, the answer is it's not the same 8 for all subjects, but I can tell you roughly which 8 are important, because I have seen this data. I didn't present the actual results, but they are available. They are available in preprints, in Bioarxiv and PRJ preprints. The papers are still due. You could just Google Nayan but Varadhan. It's in PRJ preprints and Bioarxiv. Which 8? So since I know the results, I can say from the top of my head, the distal sensors or the tip sensors intuitively are important, and algorithmically, computationally also they are important. All the tip sensors, 5 of them, are important, and the thumb sensors are generally important. And one other sensor comes in different fingers for different subjects. For mostly the common, who are the usual suspects? The usual suspects are the tip sensors and the thumb sensors, and 1 or 2 may change for the other fingers. But that's, did I answer that question at all?
Yeah. One more thing, like you mentioned, you have also done the neural network design. So like, what is there in the input layer?
The input layer consists of individual segment position displacement data. So displacements and orientation data. For this purpose, we only inputted actually 16 sensors, each give 6 component data. Displacements in 3 directions and angular displacements in 3 directions. So 16 times 6 is 96. But I'm not inputting 96 data, but I'm only inputting the orientations, not the displacements, just the orientations. 48, channel data, 48, so dimensions 48. The output is the individual joint angles between. So there are 21 joint angles. I described which angles these are. So the output is 21, the input is 48. And hidden layer can vary. The number of hidden layers can vary, and the number of nodes in the hidden layer can also vary.
So this thing you are doing with the help of MATLAB?
I'm sorry. Yes.
Yeah, that makes sense.
I want to do it with more efficient, this, but students are gifted with MATLAB, but I mean MATLAB skills, but not so much of regular coding. I mean, to take advantage of the parallelism, but the regular pair for example, doesn't really work all the time. So there are problems. Yeah, this is all done in MATLAB. Yeah.
Thank you.
I have a couple of questions.
Yeah.
So one being, you showed PCA, right? And you were selecting some top components. Those don't map individually to sensors, right? So you're not
Good
exactly
question.
using
Yeah.
PCA.
Yeah. So that's a good question. So what's principal component analysis? So just to go back to remind ourselves, what's principal component analysis? So these are fundamentally, you have some correlated data sets that's converted into, uncorrelated data sets. So that's basically a coordinate transformation from correlated data set to an uncorrelated. So you basically find eigenvectors. Each principal component is basically an eigenvector. By definition, they are orthogonal to each other. But what is a principal component? That's his question. A principal component is basically a linear combinations of several sensors input. So if I have 5 principal components, doesn't necessarily mean only 5 sensors are needed. No. It's possible that each PC has 16 inputs. So what we do, just to overcome that problem, what we do is that not all of them have equal weight of that. So we go and take a look at each of the PC and cut down those that have very low loading, very low weights. Still we have the accuracy. So yeah, that's a very good technical question. But we have to do that because our goal, as you said, is not to reduce the number of PCs, but to reduce the number of sensors. These two are not the same. So that's what we did. And we still got the accuracy. Okay. So yeah.
The second question is about this training times, the orders of magnitude of weeks and months. So have you considered offloading the, are you using GPUs?
No.
So neural networks are very well tuned for GPUs. So even for a cheap GPU, like a low-end GPU, which can be if you put off this training, it should cut down in orders of magnitude.
Correct.
Yeah. So you can consider that probably.
Absolutely. This was in the list of things for us to do. But why didn't we do it? Because programming GPUs is not trivial. There are only so many who can do it, and the student had to graduate. He didn't want to learn the art of this. He finally learned, but by the time he learned, it was like he was ready to graduate. So we used only that. And we don't, after he graduated, I didn't want to really buy a GPU, this toy for him. Anyway, it's gone. So yeah.
In the current ecosystem, you will have a lot of abstracted out things, which would be, say, for example, Python code with backend. So that would be as easy as MATLAB. A learning curve wouldn't be too high. So, but the training time should cut down to minutes and hours, like the kind of data you were saying.
No, we did check that. Okay, for what it's worth, since you're asking, we did check for a sample data set, not for the entire data set. We did check what ran for several days. Actually came down to 10-15 minutes. That's true. Yeah. But we didn't do it for every, because there's just so much analysis to do. We didn't do it for all parts of that. That's true. Okay. That's absolutely true. Okay. We have seen that also. Yeah.
Okay. Thanks.
Professor Varadhan, I have a question. Have you looked at utilizing the different outputs that come out to identify which individual it is? Are you able to correlate an individual versus the mapping of the outputs?
So, can you use this as biomarker? Can you use this like a fingerprint?
Yes.
Okay. coming from this field, I have to say that I believe that that's a possibility. And I'll be honest, having been trained in a proper kinesiology department, here is a skill that I have. That, my office is locked, people are walking on the corridor, I can say who is walking. And I can also approximately say for what purpose he is going. That is not accurate, but the first one is very accurate. I know Lakshman Rao is walking, this student is walking, just tuck, 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 that the cadence, the times, I don't see anything. I just hear their shoes, this, and I can say. So I like to believe that there are signature features of movements that can distinguish individuals. I can do the classification. Now you are asking a different question. You are asking, can a computer do that? I like to believe that we would like to build tools that can use it. But in today's world, what does it, I'm just thinking, everything is known to everybody today. There is no such thing as this. So I don't know why, because, today I just go and just to keep a fingerprint and my whole history, geography is known. Yeah, we can do that, possibly. I think that's true, that different movements can predict. We have not looked at that. But I like to believe that such algorithms can be developed, and it's possible, theoretically. And I am confident that it can be done. Whether a computer can do that, what exactly are those algorithms, I don't know. Yeah.
Thank you.
Professor Varadhan, thanks for a very interesting talk. I have just one question. You mentioned that you just arbitrarily, you just chose 8, right, with respect to sensors. So why the particular number 8? I mean, why not 9 or why not 7?
Okay. That has something to do with the experimental constraint. I didn't explain this. The experimental constraint is that I have only 16 of these sensors. Okay. My goal, and what happens with these sensors is that a problem. I should also, there's no time, and it's not really necessary for every one of you to know. A problem with this Polymus liberties sensors is that, early on when a person is doing something, right, in relatively low velocities, no problem. But when a person is very well learned and is doing very fast movements, which my subjects do, after typing, all you can see is that their fingers are moving like that, but they will be typing very accurately. Like, we do 15-day training for this, a very tough experiment, not discussed in today's talk. So all you can see is very fast finger movements, but they'll be typing very accurately, like out of this. In such high velocity movements, what happens is that these sensors break. There is a physical breakage, as in the cable that connects to the coils is broken at the point where these two connect. It's a strength of materials problem. It's a fundamental thing that we haven't been able to overcome, and that apparently violates their warranty thing. So we wanted to have sufficient cushion for finishing the experiments that we promised to the agency, that we promised to DST. So I wanted to have at least double the number of sensors. So I only have 16, so I wanted to keep it at 8. That's one reason. The other reason was that if I had 8, I could study bimanual movements. I could study 2-hand movements. So that's the other reason. So if I had 8 on this hand and 8 on this hand, then I have, my 16 can be used to study 2-finger manipulation, which we do all the time. We do 2-hand manipulation. So that was the other. So why number 8? It could be lower. Okay. Why not 7? Why not 5, for example? We compromise. So you compromise accuracy. So you need a sweet spot there. So it was arbitrarily chosen. Yeah.
So if the sensor reliability had sufficiently improved, then you could probably sort of reduce it.
Yes. Well, if I had a less number of, if I didn't have a variable number of movements, if I had a relatively small number of movements that were performed stereotypically, then I could reduce the sensors very confidently. This was a very tough task, 100 different objects, whatever, and different people with different hand sizes, people with different skills, some sports. It was tough. Yeah, but if I had a stereotypical sensor set of this, I could do it. Question?
Brain data, have you correlated this with brain measurements such as fMRIs?
Okay, no. The straight answer is no. We don't do fMRI because our system is a magnetic tracker itself. So I cannot use it in tandem with an fMRI. But what I could do, and I am doing, I am developing my own. So we are also building. So we are also big on device development, which I did not talk about in today's talk. I have built from off-the-shelf components a 32-channel EEG system. So I'm going to cut that. A 32-channel EEG system that I have built from off-the-shelf components. So I am buying another 32 channels. So as in, I'm going to expand that to about 64 or 128, and then I can study, the brain activity from a EEG perspective. But note, I'm not going to have the spatial resolution that comes with fMRI.
The challenges.
But I'll have very good temporal resolution. But the spatial resolution that you get with fMRI, I will not have. In other words, I cannot identify the exact brain regions that contribute to this activity. That's tough to do with EEG. It's not as good as fMRI. But our glove, the glove that I presented in the last few, this glove I think is MRI compatible. But I don't have a scanner available in Chennai that could do fMRI in Chennai that is available. NIMHANS has a scanner here, but I don't know if they will share. But I have colleagues in Allahabad, CBCS, Center for Brain and Cognitive Sciences, Allahabad, who are buying a scanner. So they are in the process. So when I say we are in the process of buying, we are talking about 2-3 years. So 2-3 years from now.
We can talk about it afterwards.
This is India. So in 2-3 years, we'll have the scanners.
Well, you can always come to Boston.
Sir, actually, I had a question.
Yeah.
You told about you can recognize who is walking in the corridor. Is it by the pattern of their walking?
I can do that. Varadhan can do that.
Yeah. I was actually...
No, with practice, you can do that too.
No, there is actually a software, the new Google Pixel 2 launch, right? It has a new option called Now Playing. What it does is, there's a music playing in the background, suppose. You think that you know that song. This recognizes what that song is and starts playing in your mobile. You can download it or do anything you want with that.
Oh, so like don't you think the app that's there?
Yes.
There are many apps that do that, right?
So don't you think when you think about the practical application of what you told, you need to maintain a huge amount of data of a single particular person?
Yeah. But his question is, can we get this done through apps? That's going to be tough. It's not a trivial problem. That's not like song recognition. Don't assume that, because songs have a particular structure. Human variability is way higher. So don't assume it's the same. Songs, yes. There are only, okay, I'll give it. Songs also have a huge amount of variability. But then, the structure can still be used, and you have actual data that you can use, which you cannot do that. I can not only say who is walking, I can say where he is going. Is he going to meet the HOD or is he going to meet a student?
That is the next
That's
part
a big
of
deal,
it. Okay.
right? No, because, see, there is a difference.
Yes.
So.
Professor Varadhan, nice talk. What applications do you see in sports?
In sports, in gaming, I see some applications for this glove-based device that we have developed, and our data glove that we have developed using IMUs. In sports, the accuracy that these systems have are going to be very limited. So, no, I wouldn't recommend these for sports per se. By the way, cricket is not a sport, so in any case, do we play sports? I don't know. Are there other questions? I'm going to be available for another, some time. So if any of you have any questions, more than happy. By the way, my name is Varadhan. You could just Google me. My email ID, unfortunately, these guys didn't put my email ID, I think. That's ridiculous, don't you think? Okay, sorry, I take responsibility. I should have put it. skm@iitm.ac.in. Please email me. You're all welcome to visit my lab. We don't have a lab per se. What we have is just 2 small rooms, 100 square feet each. That's where the students sit. That's where I hope they sleep and eat there also. the experimental rooms are kept separate, but we do. I mean, we are still excited about what we do. It's not about resources. It's about still the science. We are in this for the glory. So any of you, please, it's a free pass. I welcome all of you to come. Thanks to the brilliant ideas that came. Please come when you have time and drop by, show us. Tell us what we could do better. More than happy to learn from you. Thank you. You have a question? He still has a question. I could answer that.
It's kind of a fun question. So, have you ever verified your skill, like where is he going, and you followed him to verify that
Yes.
you have predicted correctly?
Yes. No, with a small sample. Yes. With a small sample size, n equal to less than 5, n equal to 4, 5. Yeah. With a small. No, there are only so many people who sit in the corridor. So there aren't many. So you need data, practice. It's not like I can do it. For example, when you walk, I can't identify. I don't even know who you are. So you need, obviously there is calibration data that is needed. Yes. So there are only so many who are there. With n equal to 4, it's easy to do. Yeah, and I have verified. Yes, I have verified. Did you go to meet HOD? How did you know? Just guess. So yeah, I have verified. So are there other? So I'm going to be available for some more time. As I said, my name is Varadhan, Varadhan. So Varadhan SKM. Just Google us and email me, drop by my lab. Thank you so much. I could take this off.
Thank you, sir, for the informative session. Thank you for taking us through your experience of conducting various experiments. Now I request Dr. Sudarshan TSB to felicitate our guest speaker with a token of appreciation.